This is AS1 January 08. A hotel lift initially at rest moves vertically in a straight line. From time t equals 0, it accelerates uniformly until t equals t1, when its acceleration suddenly decreases to 0. It continues moving until t equals t2 with 0 acceleration. It then decelerates uniformly, coming to rest at t equals t3. The top graph shows how its acceleration depends on time. And the next part of the question then asks you to draw in, on the middle and lower axes, then you are to draw in velocity and displacement time graphs for the lift. So you look at the graph above, acceleration time graph, and you've constant acceleration. Now constant acceleration is going to cause a uniform increase in velocity, which is going to be a line of constant slope. So we're going to draw in a line of constant slope there. The next part of the graph says the acceleration 0, so that means that the velocity then is just increasing in a straight line. Sorry, not increasing, I mean continuing in a straight line. And then the last part is a deceleration because it's got a negative acceleration value. Again, it's constant, and therefore the line goes down straight like that. The displacement time graph then, you've got a constant velocity here, a constant acceleration here, so the velocity is increasing. That means the displacement time graph, the displacement is increasing at a non-uniform rate. And it's because it's an acceleration, that's always an upward slope like that. The next part of the graph is a constant velocity, and that's always a straight line on a displacement time graph. So I'm going to try and just join this up a bit, like that. And then the last part of the graph, the person decelerates to 0. But again, deceleration on a displacement time graph is a curve, but this time it's a downward curve, or a curve like that, where the slope of the curve is getting lower and lower and lower. And that's your final displacement time graph. The next part of the question then says a typical jet aircraft accelerates from rest for 28 seconds, leaving the ground with a takeoff speed of 270 kilometers per hour. Show that a speed of 270 kilometers per hour corresponds to a speed of 75 meters per second. So speed is distance over time. In fact, that's not what we're going to do yet. All we're going to do is change the 270 kilometers per hour into meters per second. So that's 270 kilometers over hours. If you remember, in another question I got you to write it like that. The conversion factor is to multiply by 1,000, so that's equal to 270. The top line you're multiplying by 1,000 to make it into meters. And then in the bottom line, hours to seconds is 3,600 seconds. So that's the sum that you have to do to get your answer. And your answer comes out to be 75 meters per second as suggested. Next part of the question, assume that the acceleration of the aircraft is constant. Calculate the acceleration of the aircraft as it travels along the runway. So the information up above tells us the aircraft accelerates from rest, so u is equal to 0. The time it takes is 28 seconds. We know that its final velocity just before it leaves the runway is now 75 meters per second, and we need a. So we're just going to use a is equal to v minus u over t. And that gives you 75 minus 0 over 28. And that gives you an answer of 2.67 meters per second squared. Part 2, calculate the minimum distance aircraft travels along the runway before it takes off. And so in addition to all the things we know up in the last question, we're looking for s. So really you can use any equation, just use the simplest one. S equals a half u plus v times t. And that gives you a half. U is 0, v is 75, and t is 10, isn't it? No, sorry, 28 seconds. It accelerates for 28 seconds. And that gives you an answer there of 392 meters. 392 is your answer.